So power produced by a battery and the resistor. So we have here a battery connected to a resistor. So the power equation is the power produced by the battery is the voltage of the battery times the current in the circuit. So this is the power produced by the battery. The power dissipated in the resistor is the voltage across the resistor times the current running through the resistor. So the battery is producing some power and the current is flowing through the resistor. So if the battery has no internal resistance, which now I'm going to assume there's no internal resistance, so then all the power produced by the battery is dissipated in the resistor. So the power produced by the battery goes into the resistor, and then we can say voltage of the resistor, we can write down as current times resistance. So then there's a couple of different forms of this equation. Voltage of the resistor is I. If you substitute it, IR times I, so you get here I squared R. Okay, and also you could substitute the current, and then you could say current is equal to VR over R, then substitute that into there, and then you get VR over R, so you get VR squared over R. So you have three forms of the power equation in the resistor: VR times I, or you can say I squared times R, or VR squared over R. For the battery, you just leave it like this because there's no resistor for the battery. There's no resistance. I'm assuming there's no internal resistance. So then you just leave it like VBI. So then if the resistor is the only thing in the circuit, then the power of the battery should equal to the power of the resistor. So let's quickly derive this equation. The idea is going to be the same way kind of how we derive the energy stored in the capacitor equation. We're going to say power of the battery is the rate of work done by the battery. The rate of work done by the battery. So what the battery is doing, remember what I told you, that positive charges, their natural thing to do is for a positive charge is to go from a positive potential, from a higher potential to a lower potential. That's the natural thing. So it goes like this. So in going through the resistor, the potential energy of the positive charge is losing. It's losing potential energy. Then it's coming down. Okay, now when it comes to the inside the battery, imagine the battery is like this. So this is the negative of the battery. Think of the battery as like almost like an elevator. So the positive charge comes down here. The positive charge says, I like to stay on the bottom. I want to stay at the bottom. But if it stayed there, there would not be continuous current. So what the battery has to do is to do work on that. We could say the work done by the battery is dQ times the increase in voltage times. So remember from the work chapter, from the energy chapter, we have dW is equal to dQ times the voltage difference. Work is charge times voltage difference. So the voltage of there is V, and the voltage of this I'm calling 0, right? So the battery has to take that charge and lift it to a higher elevation against its will, right? So the work done by the battery is dW is dQ V, and now the power is going to be the derivative of that. You see? And there you have it. So dW is dQV. The derivative of dW is dQ dt V. And the dQ dt is defined as current, I times V. So that's where this equation comes from. It's the how many coulombs of charge you're taking per unit time, and you're taking them against their will to a higher elevation. So that's why I say think of this as an elevator. The elevator takes people from down here, and then people get inside of it, and the elevator lifts them to a higher elevation. You see? Then if you leave the people there, they can go to their classrooms or whatever to the second floor, and then they can go down by either taking the stairs, or they could also go down the elevator too if there's another battery there, right? So objects would naturally prefer to go down anyway. It's not like you're gonna, after taking you to the second or third floor, it's not like you're gonna live there. You're eventually gonna come back down to go to somewhere else, right? So your natural tendency is to go down anyway, but the battery's goal is to take you up to a higher elevation, you see. So it's taking you to a higher plane than you would prefer to be, right? So that's how you derive this equation. So you just simply say dQV, then take the derivative dQ dt, and then dQ dt is defined as I. Okay. So, for example, if you apply this to things like light bulb, so light bulbs, their power ratings are based on, in the United States, are based on 110 volt or 120 volt. So imagine you have a 110 volt or 120 volt source, because that's the source that we get from our power outlets. Of course, it's AC source, but right now, don't worry about the fact that it's AC. So then if you take a light bulb that's rated as an incandescent light bulb, so it's got a little resistor in there, right? So imagine this resistor is your light bulb right here. Okay, so if its rating is 60 watt light bulb, what does that mean? Well, that means only if it's connected to a 120 volt source, only then is the power output at 60 watts when it's running at full voltage, you see. So from there, we could actually calculate the resistance of the light bulb. We can look here. We could look here at the power of the light bulb and say, okay, this is 60. And you look at these three equations. In this case, the easiest one to use is this one. So if I don't want to have to calculate the current in this circuit, right, then I can say, well, what's the resistance of the light bulb? Well, the power is 60, and then the voltage, it's intended to run at 120 volts. So 120 squared, and then that's divided by the resistor, and then we can calculate the resistance of the circuit. So then this is the resistance of the 60 watt light bulb. So that's going to be 14400 divided by 60. And the resistance is going to be, let's see here, 240 ohms. Okay, how about if the light bulb was 120 watt light bulb, twice the power rating? What would that mean? So then what would its resistance be? So then here you double the power. So you see I'm using this form of the equation. Power is voltage squared over R. So if you double this, So then the internal resistance is VR squared over P R 120 squared over 120. Resistance is going to be 120. So it's kind of like, depending on what the power is, if I double the power rating of a light bulb, its resistance is halved, right? If I double the power rating, so this is a 60 watt light bulb, and this is a 120 watt light bulb. Okay. So this has twice the power rating, so half the resistance. So what does that mean in terms of the equation rho L over A for the equation that we saw yesterday? If you're using the same kind of wire inside, half the resistance would mean what? Either half the length, so this has to have half the length of that, or it could have twice the area. It could be a bigger. So depending on how they want to make it. Let's see here. The filament inside is, the wire inside is usually called a filament. Let's see here. Okay, so you can kind of see here, this is a vintage one. It's nice. You see here, the wire. Okay, you can kind of see the length of the wire. We blow that up. Looks pretty thin, huh? 20-volt light bulb, does the filament have greater? You see here what it says? 120 watt light bulb has less resistance, and their filament is subject to breaking more often than 60 watt light bulb. Therefore, in my opinion, to get more luminaries, I recommend 260 watt bulbs over the use over one. Oh, okay. 3-way bulbs have 2 filaments. Switch one, turn on the higher resistance filament, which gives you less luminaries. So what are they saying? The 120 watt light bulb has less resistance. So we are correct, right? But they're subject to breaking. Why is that? That's because they're longer, right? No, hold on. That's because if they have less resistance, that means they are shorter, right? And or their area is bigger. Well, the area is bigger wouldn't cause them to break more easily. So why is it that they're subject to breaking more? Probably the fact that they allow more current, so that enables the wire to heat up more quickly. In other words, I think in this case, it's not the physical ailment. It's because they allow more current, and the wire heats up more, cools down more, heats up more, cools down more, and then over time that wear and tear makes the wire break. You see, that's the reason why. Yeah, you see there, they're calculating the filament resistance would be higher in the 60 watt light bulb. You see the 240 ohms versus the 120 ohms.